All right, cool. Hello, everybody. Today, I'm going to be talking about correlation power analysis, which is part of a specific type of power analysis attack, which my undergraduate capstone this semester, I was lucky enough to be able to do power analysis attacks for Professor Ziming Zhao. Jim is also in my capstone group this semester, and he thinks this is his last semester, but just because I love him so much, I'm going to make sure we fail, so he has to come back next semester for you guys. So he'll be giving another presentation next semester. Woo! Let's get started. All right. Who the heck am I? I'm a BSMS student. I like crypto. I've been getting into it more and more. I actually did well in that class somehow. One of the few classes I did do well in. I'm not good at sleeping. I'm going on 2 hours of sleep right now. I was a secretary for RC3. I did some CA thing for RIT-Sec last year. I don't really know what that was. And I play with servers every now and again. So what's the agenda for today? First, we'll talk a little bit about power. We're not going to talk about power analysis. We're going to skip that. AES, we're going to review that for about 3 seconds. We'll talk about correlation power analysis and a CTF challenge that I wrote. If anybody not from RIT is watching, thank you for coming to listen. This is my write-up. I'm not posting it on GitHub. Sorry. And then we'll do a demo with the help of RIT-Sec infrastructure. So first, power analysis. What is it? So there's these things called sidechannel attacks. They're attacks that are focused on the implementation of something and not the thing itself. So AES is like really secure. People have been hammering away at it for like 2 decades now almost. And there's pretty much no real good brute force attacks that reduce the key space to anything meaningful. So right now, the AES key space is absolutely huge. And if somebody tells you to brute force even an AES 128 key, which I guess technically AES is only 128 bits, but whatever. That's not really relevant right now. You're not going to be able to brute force AES is the point. So looking into how you could attack the implementations is much more interesting. Turns out, power analysis is a type of sidechannel attack. So when you perform an encryption operation, or really any operation, your processor uses energy, right? That's why our batteries frickin' die. That's why when you're in a VPN tunnel and you're doing a lot of traffic, battery's going to go down and your CPU is going to be using a lot of stuff. It's sad. However, different operations use different amounts of power, right? So if you're traversing different paths through the processor, if you're using different components like different adders or muxes or whatever, each one of those is going to use a different amount of power. So you can sort of, kind of, theoretically, like fingerprint specific operations on the processor based on how much power it's using. This isn't really practical for something like a laptop or a server or a phone. Oh, excuse me. Because it's doing a lot of things at once. But for something really small, like a smart card, it's useful. So power analysis, it's based off of these things called power traces. This is an example of a power trace that we captured for an AES 128 operation. It's just the encryption of one block. You're sampling the power usage of whatever device over time. There's a couple of ways to capture it. And if you care about this, you could take the class that Professor Zhao is hopefully going to teach with this course material in I don't know how many semesters. That's kind of the point of our capstone, but I don't know when it's going to be coming out. So once we capture these traces using magic that you will learn in that class, maybe not, I don't know. You can use it for power analysis, which there's a few different methods. There's like differential power analysis, which there's a few different statistical methods of doing that, most of which I don't understand because I did bad at statistics. But there's also correlation power analysis, which I do understand because it's relatively simple and it doesn't use weird calculus. So correlation coefficients, quick review. This is For correlation power analysis, we use correlation coefficients. It's like the single most important statistical thing that I want everybody to know. The correlation coefficient shows how much two sets of data correlate with each other. So here we have this green line and these orange dots in a few different sets. So P, we're going to call it P. I think that's rho. I don't know. When P is -1, it shows that there's a very close negative correlation between the data set and between one data set and the other. So like when one data set goes down, the other one goes up, and that's a very close correlation. When it's +1, that's a positive relationship. So when one data set goes up, the other one goes up. I don't really know what the green line relationship, whatever. The smaller, the closer to 0 the correlation coefficient is, the less of a actual correlation there is. So with this, dots are kind of all over the place, don't really know what's going on, doesn't really look like a line, doesn't seem to be any meaning in this data. Whereas over here, it's very obvious that they're in a line. So what I want you to get from this is that the further away the correlation coefficient is from 0, i.e. its absolute value, hey, math, the bigger the absolute value of the correlation coefficient, the more correlation there is. Remember that. That's important. All right. Next, we're going to talk a little bit about AES. Yes. All right, so AES, it's a block cipher, which means it operates on blocks or chunks of data at once. In the case of AES 128, or I think the other sizes as well, it's 16 bytes. Don't quote me on that. I know it's 16 bytes for AES 128. One of the steps that AES does to do all the bit messing around to make your traffic to YouTube secure is the Sbox. This is like a lookup function. It takes an input, and then with that input, it gets an output. So for this, let's say your input is in hex E7. So you take the E, that's a row. You take the 7, that's the column. Where they intersect is your output. So in this case, it would be 0C. So for an input of E7, you get an output for the Sbox of 0C. Awesome. Moving right along. Then, so where the Sbox is used, it's right at the beginning of AES. This is kind of a zoomed in version of a diagram of showing what AES does. You see all these different pieces. This is the different bytes of AES. So like this would be the first byte of the plain text in the key working on right here. This would be the second byte. This would be the third and fourth and fifth and so on. OK, so what's going on here right at the very beginning? So P0, that's the first byte of the plain text. R0, K0. Why there's an R0, don't worry about that. But that's the first byte of the key. So what's going on here is it's taking P0 and K0 and popping them into that little circle with a T in it. That means XOR. It's taking the first byte of the plain text and the first byte of the key and XORing them together. Then it's using the output of that as the input to the Sbox. The output of that Sbox is this red dot that I added here. This is called the intermediate value. It has no meaning whatsoever for AES, but it has a lot of meaning for us. Remember that intermediate value. It's the output of the Sbox. All right, now we're going to get into the meat and the potatoes, the interesting stuff. Correlation power analysis. Does anybody have any questions so far? No. OK. So correlation power analysis is one form of power analysis that I discovered one night and decided this would be a cool CTF challenge. And it's a great excuse to make a CTF challenge while also working on Capstone. So I created a challenge called Evil Accountant, CPA, correlation power analysis, bad joke. So the idea in the Evil Accountant challenge was you were given a base 64 encrypted ciphertext and a zip file that contained a JSON blob of power traces and plain texts. And using correlation power analysis and a little bit of brute forcing, I'm sorry, you would be able to find the key that encrypted the ciphertext and then decrypt it to get the flag. We're going to talk about how that works in 5 easy steps. First up, you generate these power traces by encrypting single blocks, doing like a single round of encryption with AES 128. You don't know the key, you just know the plain texts. And we're going to talk about each one of these in depth in a minute. After that, you create some kind of modeling function for power usage. You give it an input, and it gives you some kind of value that's like, we should use this much power. 3, estimate the power usage for a key guess. So now that you have your modeling function, you got to guess, OK, if the key is this, how much power do I think is going to be used? Excuse me. For 4, then you find correlations between your estimates that you generated with the modeling function and the actual things that you measured via the traces. You try to correlate those values. And then 5, with those correlations, you pick the correct key guess based on which one has the highest correlation. If this sounds a little confusing, it is. So we're going to talk more about them, each one of these steps. So first up, we got to generate the traces. And you do that by encrypting one block at a time in ECB mode. If anybody remembers modes of operation for block ciphers, there's a bunch of them. ECB mode is electronic codebook mode. Don't use it. If some of you might have seen a picture representing why it's so bad, they take the Linux tux and then they encrypt it. And you can, the colors are all weird, but you can still kind of see what the penguin is. Turns out, not only does that work for pictures, but you can also figure out the key when something's encrypted with ECB mode if you have the ciphertext as well. But that's a completely different attack, and maybe I'll talk about that next semester. But for this, we're just generating, we're going to do some random plaintext, and then we're going to give that plaintext to some black box, i.e. a smart card, that has an AES key. We're going to tell it, OK, encrypt this 16-byte plaintext block and give me back the ciphertext. As it's encrypting, we're going to somehow magically capture some power traces that are going to tell us roughly how much power is being used at each point during the encryption. Then, once that's done, we're going to save the plaintext, throw away the ciphertext, we don't care about it, and then also save the power trace. We're going to do this 50 times. Only 50 times. AES is really fast. It can encrypt a lot of blocks really quickly. So if you only need to encrypt 50 blocks, think about like for a real life attack, if you had a smart card that you were trying to get the key off of, and somebody just left that thing sitting around, plug it into your laptop, run a script, take a couple seconds, pop it back out, boom, done. You got your traces, move on, nobody is the wiser. Don't actually do this. 1, it's hard to do in a real environment, and 2, I think most real smart cards are supposedly not vulnerable to this anymore. Most of the research happened in the early 2000s on this, so it's old news now, sorry. Also CFAA. So once you get your traces, then you create some kind of model for the power usage. The input is going to be that intermediate value we talked about, the output of the Sbox. The output of this function is going to be some unitless scalar, which means just a number, just some random positive number. It doesn't have a unit. It means nothing by itself. It only means something in relation to other numbers. So it could be like 5. Great. I don't know what 5 means, but if I have 5 and 3, I know that whatever generated the 5 is using more power than whatever generated the 3. And we have some kind of ratio of those two. So yeah, the output, whatever that scalar value is kind of like an estimate of how much power would be used to generate that intermediate value. So if you have a certain byte of plain text and a certain byte of key, how much power is going to be used for that encryption operation. And since we have the plain texts, we can guess the keys. We're going to get to that in a second. For the power model that we're going to use, we're going to use Hamming weight, which is really just, a count of the number of ones in the binary of the number. So if our intermediate value is a byte, which it's a byte, it could be anywhere from 0 to 8. There's reasons for this. I'm not going to get into it. I don't really understand it, but it's been experimentally proven to work by smart people and also by my dumb little script. So now that we have our power model, we have to estimate how much power is going to be used for a specific guess for the key. So to do this, first we have to have our key guess. And the way this works is we're going to work on the key one byte at a time, which we'll talk a little bit more about later. So if we're working on the first byte, we're just going to guess, all right, what's a value that's possible here? And to do this, we're really just going to do all the different possible values from 0 to 255. So you're going to take whatever guess that you're using and compute the intermediate value. And you're going to do that by taking your byte of key, and then for all the plain texts you record, let's say you're going to pick the first plain text first. If I'm working on the first byte of key, I'm going to take the first byte of plain text and XOR those together. 'Cause I don't know if you remember seeing in the diagram that was blown up over there a little earlier, the first byte of plain text and the first byte of key, those are XORed together. Same thing for the second and the third, and so on and so forth. So we're going to do that, XOR them together, use that as an input to an Sbox lookup. Boom, we got our intermediate value. Then you're going to run that through the power model. So you're just going to get the Hamming weight of it. And that is going to be our estimate of power usage. It's kind of rudimentary and lame, but it does work. And then what we're going to do is we're going to do this for every single plain text and every single key guess. So for every byte, 0 to 1 to 16, and for every different possibility for all of those key guesses, 0 to 255. And then for all 50 plain texts, we're going to do this operation. Does that make sense? Is anybody confused? Am I going too quick? Am I going too slow? Are the memes lame? Is everybody dead? Yeah, I know, it's been a long semester. All right, number 4, drink. So now that we have all of our estimates, oh, yikes. That should be 3, not -3. It's not possible to have -3 ones in a byte. Whoops. So now that we have our estimates, this is, so if we have a key guess of, let's guess that our byte is 128. When we ran it through, did the Sbox lookup in the power model, let's say with the first plain text, that gave us 4 ones in the intermediate value. The next one might have given us 7, and then a single solitary 1, and then maybe 3 ones, and then 5. You get the idea. Then for our measurements over here, this is actually a sampling of the measurement values that you guys were given in the traces, if you did the challenge, sorry. So the way this works is each column is an individual trace. So like trace 1, this is the trace, this is the power trace for when we're encrypting the first plain text. Trace 2, second plain text, trace 3, third plain text, and so on. And then each row is a separate data point in the trace. So a trace is just a big, long list of data points. You could roughly correlate these with time. It's not like it's 1 per millisecond or anything. Well, it sort of is, but whatever. So data point 1 is first, then data point 2, then 3, and then 4, and so on. All right. We got all of our data. It's not big data, but it's some data. So what we're going to do is we're going to take our set of estimates and correlate them with one of the sets of measurements. And we're going to do this one data point at a time. and we want to correlate the it's kind of complicated. Basically, what's going to happen is, if we go back to this graph, you could say this first dot, or like right here, is plain text 1. So like maybe that orange dot is our estimate. And then maybe we'd have another dot somewhere around here for whatever the trace value was for that plain text at data point 1. Same thing for the second plain text. That orange one is our model or our estimate for the second plain text. And then we have some trace measurement around here for the second one, and so on and so forth. So we're going to correlate those two values and see how closely they're correlated. Is there no correlation? Like, are we just wasting all of our time here? I promise we're not. Great. So we're going to correlate those two using something called Pearson's correlation coefficient, which I think we might have covered, but I got a C in ProbStat, so I don't remember. It's going to give us a correlation value, or a correlation coefficient. Great. What does that mean? We'll get to that. Then we're going to do the same thing. We're going to take the estimates, correlate them with the second data points, get another one, and another one, and another one, and another one. Awesome. So once we've done this for all of the data points and all of the traces, and the traces that were given had 1,530 data points in them each, so it's a lot of computing. Now we have to pick what is the final correlation coefficient that we're going to use to represent this key guess. Because what we're doing here is we're trying to eliminate the factor of time. We don't really care where our model correlates with the measurements. We just want to know where it correlates the most. And so by doing this, we're essentially correlating it with each point in time during the encryption operation and picking out the one point where it matches the most. And in this case, what do you guys think? Where does it correlate the most? Anybody? Is it the 61? Is it negative 85? Is it 0.38? Any guesses? Negative 85. Hey, Jim, who's in my capstone group, knew that. Yay! Because a higher correlation is a higher absolute value. So negative 85, maybe that, like that value itself, or negative 0.85. Maybe that value itself is less than 0.61, but it represents a higher correlation because it has a higher absolute value. Yeah?
Okay, so the absolute values are what's relevant and not like, or the correlationary result from getting the correlation value across the table? Absolute value of that is what matters.
That is correct. We don't care if it's a positive correlation or a negative correlation or a left or right, up, down, strange, charm correlation. We just care what kind of correlation it is and how, or we just care, excuse me, I just said we don't care what kind it is. We just care how strong the correlation is. So in this case, for this key guess, whoa, that was quick. The correlation value is 0.85. Cool. So you go through all of that for all the possible key guesses, and then you do that for all of the bytes in the key. But how do you pick the right key bytes? How do you put together the key so you can decrypt the plain text, get the flag, get the points, get that sweet dub, and move on with your life? Here's how. So we guessed the key and separate, we covered that. So each one of these 1 byte chunks, I'm going forward, call subkeys. Sorry, subkey means something else in the context of AES. But here we're just going to talk about those 1 byte chunks of the key. So we're going to have 16 subkeys. So what we're essentially doing here is kind of like a brute force, except it's a much better brute force because we only have to do 4,096, we only really have to test 4,096 different possibilities. Unlike with a dumb brute force, where you just try every single possible key, it's a number that is big enough that I didn't want to put on this slide, so there's the exponent for it. And the reason that this works, guessing 1 byte at a time, is because we only care about getting power estimates and right now, not actually decrypting. So like during a normal brute force attack, what you do is you try a key, you decrypt the plain text, the ciphertext. You say, all right, does this look like what I'm expecting the plain text to look like? No? Okay, try a new key. And working on a byte by byte for that doesn't work, because if even one single bit in the key is wrong, then the plain text is going to look completely wrong. It's not like there's going to be some words misspelled, or maybe the last little bit is going to look wrong. The whole dang thing is going to look wrong. But since we're doing power estimates, the power usage of 1 byte is going to influence the overall power usage. Because if you think like the power usage of computing that intermediate value overall is just the aggregate of the power usage of each of the 16 individual bytes, if that makes sense. I promise it works if it doesn't make sense. I promise it does work. So then what we do is we get the final correlation value for each possible value of the subkey. That's what we did in this previous step, the .85. And then for a single subkey, so like say for the first byte in the key, for all of the possible values of the subkey, we're going to pick the one with the highest correlation. So for this subkey right here, whatever this guess is, let's say 128, if there are no other values, so if all the values between 0 and 255, if of all of them 0.85 is the highest final correlation value, then we can be pretty sure that this subkey is 128. Note I said pretty sure, not certain. It's an important caveat. So then once we do that, for all 16 subkeys, we should, in theory, have our key. All right, now let's look at some code, because code is always fun. Not really. So this function is going to determine, oh Christ, what the correct byte is for a given subkey. So we're working with the byte index. This is the index of the byte in the key, so 0 to 15 inclusive. And then for each possible guess between 0 and 255 for that subkey, we're going to get the final coefficient. And if that coefficient is higher than our current maximum, then we're going to save that subkey guess and essentially just return whatever is the highest, or whatever subkey guess has the highest final coefficient. Whew. So what does this look like? In a good case, so this is the example for byte index 1. If you graph out all of the different final correlation values, it would look something like this. You got a bunch of stuff that's just kind of noise, and then one little outlier right there. We can be reasonably confident that that outlier that's way above everything else in correlation value is probably the right one. And I'll tell you right now, it is correct. What happens if you get something like this? This is byte index 3 that you would find with the traces for this challenge. This made some people upset. So there is, in fact, one value over there, right there, that is that has the highest correlation, but it's not that much higher than everything else. And if you notice, the maximum value on that y-axis there is a lot smaller than the maximum value on this y-axis, 0.8 versus 0.6. Interesting. All right. So this is the function that actually does the correlation. It's pretty much the code version of that dope-ass animation that I put together for you guys with the blue boxes earlier, which we already talked about, so I'm not going to go through again. Only dope thing is the Pearson correlation coefficient thingy. You don't have to actually implement that. SciPy has that for you. You just have to compile SciPy, which takes a little while, sadly. So now we're going to do a demo. And it's going to take me a couple minutes to set this up. So if anybody has any questions or comments, now is your chance. Why are there no shit posts going on right now? I'm sad. As long as it took me to make it in GIMP. There was a 2 and a 0 and a 4, so I just did some moving around and scaling. All right. Where is this? Okay. Where's that? 4? 4. Whoa, hold on. All right, cool. Ignore this. All right, I think this, can everybody see this? Hello. Who am I? Hi, cool. All right, you can all see this? So, right here we have my repository. This is actually public now, so you can download this all and run it yourself. We've got, well, check out the Readme. It's got the challenge description. Oh boy. All right, so title, Evil Accountant. Author, Neon Spandex, that's me. The flag is correlation can sometimes imply causation, and then some padding because I encrypted it with ECB mode AES and I didn't pad it, so whatever. So that's the flag, and then here's the description. Your CPA sent you a message encrypted with 128-bit AES, but refuses to send you the key to decrypt it. A few days later, their maid sent you a strange JSON object in an email, and they CC'd someone named Pearson. Here's the ciphertext. Oh, this is an older version of the description. Okay, so originally what I was going to do was give everybody the bytes at index 0, 3, and 4. Now, if you remember that graph I showed you, that was with the one that didn't have any outliers. That was the byte at index 3. We'll get to that. Yeah. Okay. But so there was one file provided with this challenge, traces.zip, and inside of it is just a big JSON object. But we're going to run our little attack script, not MITRE attack, sorry. And then we're going to just do a little bit of multi-threading. What? Oh, whoops. Got to activate the environment. Cool. All right, so I printed out the actual key in hex because I had the key and I just wanted to debug this. And this is going to take a hot minute. This is going to take 2 minutes. It takes 3 minutes on my laptop, which is why I'm not running it on my laptop. But what we're doing here is we're going through and determining the most likely value for each subkey, starting with the first byte in the key and working through to the last byte of the key. And what you see it printing out, so like right here, for byte at index 0, it thinks it's CB in hex. And it's got a coefficient of 0.61. Here's the byte at index 1. That's the graph that we saw with the one outlier. That's got a 0.85 correlation. Here's 0.84. This is byte at index 3. This is one of the ones that, or this is the one that I showed you with the graph that didn't have the outlier. This is the one with the outlier. That's the one without the outlier. Interesting. Also, if you look at this one and this one with the low correlation values, and if you compare them up to the actual key bytes, you'll notice that they're different. Very interesting. And then these ones with the higher correlations, you look up, oh, those are the same. All right. This is a problem. We're not getting the entire key. So these ones are, this byte, that one looks incorrect. this byte looks correct. That one's correct. This one, incorrect. This one is incorrect. Correct, correct. We got that one. We got that one. We got that one. And we're going to get the rest of them because I've already done this, so I know what's going on. So we have all but 3 of the bytes of the key. The bytes at index 0, 3, and 4. And originally, I was going to give everybody those bytes. But I was told, that's too nice. This is a CTF. You got to make it hard for these people. You got to make them work for it. And I was thinking, oh, yeah, you could just Google it, and there's code out there to already do it. And then only 9 teams got my challenge. So maybe I made this too hard. I don't know. But so once you do this step, if you try to decrypt it, it's not going to look right. So what you have to do after this is look at the correlations for each one and pick the lowest of them. It's really easy if you look at a graph of all of the graphs that I showed y'all, because it becomes pretty obvious which bytes have outliers and which bytes don't have outliers. Like some of these are quite a bit lower, like 0.74 is a lot lower than one of them is like 0.91. Yeah, there's 0.91 one over there. So, but if you look at, so like just from looking at it that way, you don't know which ones could be wrong, but looking at the graph, you could kind of tell. There's also the very last byte was 0.66, which had some people waste some time because they thought they'd have to brute force 4 bytes. You only had to brute force 3 bytes. This one, and this one, which is only 24 bits. I think that's something like 16 million different key combinations that are possible, which sounds like a lot, but I tested on my laptop. OpenSSL can do over 100 million rounds of AES in under 3 seconds on my laptop. So that's like 0.3 of a second to brute force it all, which isn't that bad. But a lot of people freaked out because they were like, oh, my laptop's slow. So anybody who asked for help, which was a majority of the people who solved the challenge, I took pity on them and said, just don't brute force the last byte. Only brute force those 3. Trust me on this one. And then they all got the flag. So that was cool. Yeah, there's the demo. Where is our slides? Here's our slides. And that's it. Finn.